Chapter 5, Processor Fundamentals. What are you going to learn in this? By the end of this chapter, you should be able to show understanding of the basic von Neumann model for a computer system and the stored program concept. Von Neumann is a German mathematician who modeled this, who gave the computer model first. There were so many models, but this one's model only is being followed today. So we are going to understand that, learn and understand that model. And that is called the stored program concept. Before that, there were many machines, but the program could not be stored. Show understanding of the purpose and role of registers, including the difference between general purpose and special purpose registers. So these are in the CPU. Now, when you say processor fundamentals, we are learning about the CPU, Central Processing Unit. So there, inside that you have short registers, small, tiny places, areas called registers for data. You store a little bit of data and then do some calculations. That is how inside the processor, the calculations, storing and all that are done, taking the results and outputting. All that is done inside this, and they are very fast processing because it's inside the processor, including the difference between general purpose and special purpose. So there are two kinds of registers. So this register may be sometimes just 1 byte or something like that. Depends. There's no rule for that. On the architecture. Architecture is the design of the computer. Like a house, when you build a house, the architect will design the house. How will it appear? So there are two kinds of registers. One is a general purpose register and the other one is a special purpose register. And you will also understand the purpose and roles of the arithmetic and logic unit, which is called ALU for short. And you know very well about these things, ALU and the CU, control unit. System clock. I don't know whether you know about it, but there is a clock ticking inside the CPU, and immediate access store, IAS, immediate access store, how the memory is handled. These are the things which are in the CPU. Show understanding of how data are transferred between various components of the computer system using the address bus, data bus, and control bus. You use the bus to transport passengers, right? Normally, you use the bus to transport passengers, or maybe vegetables, food stuff, and all that from certain areas. So there are buses in the computer also. There's architecture carrying signals, like wire, carrying electrical signals for address, which have some meanings, right? Not just haphazard random currents going this way, that way. You get a current shock and not like that. This is the signals are significant. What are they? Address bus. Address is like in the memory address, you have memory is divided into addresses, memory cells. So those are carried in one bus. The data is carried in another bus. All the data. But when you access an address of the memory, there is some data in it and you have to carry it. So for that, the data bus is there, and control bus, that is all the control signals. Do this, do that, turn right, turn left to the bus driver, something like that. Inside this also CPU, do this, do that. All those things are done by this, sent through this control bus. Then you will also understand how factors contribute to the performance of the computer system. Performance is like not like how you sing a song or give a speech or something like that. the efficiency of the performance. The computer performance is input data, process, output, and store if necessary, like that. But how do you do it? Do you take one day to process a stock control system or some kind of project? Then, of course, it's out of the question. It has to be very quick. Computer has to be very quick. So, what is contributing towards this? The speediness or fastness, efficiency of the computer. What are the factors? Understand how different ports provide connection to peripheral devices. Peripheral devices, you may have heard this in the lower classes, but do you remember them? Peripheral devices are the devices connected to the computer, the printer, the monitor, keyboard. Those things are the peripheral devices. So, how do you connect them? You may have seen the uh, mouse connected with a USB port, not the laptop mouse, but then if you have a desktop, if you in your school also you might have desktop or somewhere you will come across. There you have to connect the mouse, the keyboard, and any other USB port, any other light or chargers or camera when you connect. So there to connect, how do you connect? You can't just connect wires and all that yourself. You have to have a certain like plugging system. A plugging system. If you want to light a bulb from plug, you plug it to a plug point. There you have the microwave, washing machine, like that. You have the connection. How? What are those things called? Those ports. Now in the plug, when you plug into the wall socket, it's called the base, plug base. But the wires are that connected to the device, that is called the plug top. The 3 pins you have, 3 or 2, and that's called the top plug top, and the holes there on the socket at the wall, that's a plug base or the wall socket. So same way, the computer also there is a base or the socket where you can connect these peripheral. Those are called ports. Understand how different ports provide connection to peripheral devices. So USB is one port. Describe the stages of the fetch execute cycle. FE, fetch execute cycle. Fetch a pail of water. You may have heard, no? Jack and Jill. Fetch a pail of water. Bring or get. Get a instruction, then execute it. That's the CPU's main job, isn't it? So that cycle also you will understand. Before execute, there's a decode also, fetch, decode, and execute. There's another stage there. And understand the purpose of interrupts. There are interrupts. Like how you interrupt the teacher when the teacher is teaching, the children, the students interrupt the teacher. So like that, computer also, when it is performing, there are interrupts coming from the keyboard, come from the disk drive, DVD drive, any other thing connected. For example, there will be an interrupt in printer saying it's out of paper, ink, out of ink, is jammed, or the DVD driver, the door is not closed, or it's defective. That kind of messages come, so the interrupts. So how you handle those interrupts also, you will learn. Now let's get to the details. The von Neumann model of a computer system. So John von Neumann, that's the name who made this, designed this architecture. And what are these? The basic features of it is, there is a processor, the central processing unit. Oh, we know that now, isn't it? You don't have to tell us that. We already know in grade 4 or 5 or 6, we learned that. CPU. The processor has direct access memory. Direct access memory. So which means we have to learn. We have to learn from these things. What is not said. They are stingy. They won't give you all the details. We have to learn something from this. Does it mean that there is indirect access also? Yes, there could be, no? The processor has direct access to memory. Direct access to memory. Right? So let's just keep that in mind. The memory contains a stored program which can be replaced by another at any time, and the data required by the program. Let's look at that statement. Serious statement. We'll have to take it little by little. Memory contains a stored program. If you have a game or if you have a presentation, a song being played, or you are typing a document, uh, whatever thing, as a program. For example, this browser. Now you are looking at this, your browser to see this, or you are playing this video on your video player, media player, and you are seeing that is also a program. So when it is being working, when it is working, it's stored. The program is stored in the memory. So what is this memory? You know what RAM is? RAM. You have heard of RAM. So this memory will have this program stored in it, which can be replaced by another at any time. So if you want to stop this word processing and start graphic or video editing or sound editing, you can quickly replace it, take it out, and then start the new program, which will be stored again in the memory. Because without being in the memory, the CPU can't do anything. CPU, though, the big man CPU, the brain of the computer, but without the memory's contribution with the instructions and data, it's hopeless, helpless. Nothing can be done by the CPU. So, and data required by the program, the instructions as well as the data. That is very important. The memory must have the program and the data. Otherwise, the CPU can't do anything. That program cannot be run. The stored program consists of individual instructions. Stored program, like you have done Python, I suppose. If not, we'll be doing some programs, and that program is stored. And that program will have individual instructions. Put 10 to A, put 20 to B. There are two instructions on those things. And then add those two and put the answer to C, third instruction. Now display another instruction. So individual instructions. The processor executes instructions sequentially. So let me explain this again. The stored program is individual instruction. That means you can't say input two numbers and output the total. You can't give like one instruction like that. You will have to give individual instructions, as I told you. For that one, 4 instructions. And the processor executes instructions sequentially. In sequence, the order, in sequence, sequentially. It won't jump and take something that it fancies. This instruction is easier to execute. I will do that first. You can't do that. So then central processing unit architecture, the CPU architecture. Here is a drawing, nice drawing. And a little bit of explanation. In order to understand how the von Neumann, they say von. In German, V is pronounced as F. Volkswagen is spelled V-O. Right? Von Neumann model could be put into practice in a real computer system. We need first to identify the individual hardware components of a CPU and define their functions. Let's consider a system that has the minimum number of components needed. So this figure 5.01, this figure gives a simplified schematic diagram of a processor. Look at it. The control unit, that is CU, arithmetic and logic unit. Very nice sounding term, no? The component ALU, CU, ALU, and all the two U's are in the CPU, right? Remember like that. Control U, arithmetic and logic U is in the CPU. And the buses, we talked about three buses. Can you remember? Control bus, address bus, data bus. Hmm? So now, little by little, we are getting deeper and deeper into the CPU. This is called, you will know it later, but MDR, a register. Remember we talked about registers? MDR, memory data register, data. Then address bus, memory address register. So easy to remember. MAR, address register, the data register. Data register going to data bus, through the data bus. The address register is getting data from the address bus. And PC is not personal computer here. PC is called the program counter. Right? Program counter, because there are those instructions, program instructions are kept in addresses, memory addresses, right? And each instruction has a number. Instruction 100 is this, instruction 101 is this. So you have to keep a counter so that you will not miss any instruction. So you go one by one. After executing one instruction, you add one, right? PC equals PC plus one. So then the next time CPU knows that, okay, this is 101 now, I have to execute. Things like that. CIR, current instructions register. What is the currently executed the instruction that will be stored here? I told you again, these are registers, small memory registers. They are stored for storing. The instruction is stored here so that the control unit can execute it. There are other registers also, and these arrows show how they communicate. ALU and CU both ways, and control bus, control unit both ways. This is only this way, no? From the control unit, nobody is controlling the control unit, no? Control unit controls the others. So this will send signals there. He will not listen to any of these. Right? That is why he is not getting anything back. Yeah, you better do this. I'm not going to listen to you. You better carry out my instruction. And of course, there's a direct thing also to memory address register as well as direct to PC. Then here also both ways, MDR and other registers. This is one way. From the data, this is an instruction. In the MDR is an instruction or data. So if it's an instruction, it goes to CIR, which is called current instruction register. So this will take this current instruction register only and execute. It's quite nice if you and try to remember. Remember, you have to repeat this. Look at this again, no, in your mind. And also, after some time, see whether you can draw this. Definitely, you will not. I'm sure you will not be able to draw. Not because your memory is bad, you are not intelligent, not because of those things, but simply because you are a very busy person. You have a lot of work. You have a lot of things to worry. So please try to draw this again after the lesson. See whether you can draw. If you can't, never mind, that's good. If you can't, it's good because you are learning. If you can, then you might make a mistake later. But now, if you make a mistake, then you learn it from this point. Repeat it. And this, the recording is a very advantageous thing for you because you can go through it several times, isn't it? And go through it several times. If you miss something, if you don't remember something, you can refresh your memory with this. Please make use of this recording. The dotted outline shows the boundary of the processor. The logical arrangement of sum some of the processor components is indicated. The arrows show possible directions of flow of data. We discuss about it. As the following discussion will show, the data for some of the arrows is actually an address or an instruction. However, in general, data might be an address, an instruction, or a value. Okay, an address. It can be address. If it's an address, where will it be? It's here. The data bus will carry from the memory and put it here. If it's an instruction, it will come here. And if it's a address, it will be there. So like that, what are the three things? One could be an address, another thing could be a data or instruction. So in general, data might be an address, an instruction, or a value. The active components of the CPU. What are the two active components? You have the ALU, you have the CU. CU, not see you later. CU, ALU, internal clock, or system clock. There are two things. And the registers. Registers also there. Two components of the CPU that have an active role in it operations are the arithmetic and logic unit or arithmetic and the control unit. That of course we must have repeated 100 times. So these two. As its name implies, the ALU is responsible for the arithmetic or logic processing requirements of the instructions in a running program. Control the logic and the calculations and all that. The functions of the control unit are more diverse. Control unit is more advanced than the ALU. I mean, more work. They are also it's advanced, but limited. The number of operations. But here there are many ways on many things. One aspect is controlling the flow of data throughout the processor and the rest of the whole computer system. So doesn't it show that a whole lot of things to do? Control the flow of data throughout the processor and the rest of the whole computer. Another is ensuring that program instructions are handled correctly. So, what a responsible job. A vital part of the control unit is a clock that is used by the unit to synchronize processors. What is that? What is synchronizing processor? Now let's see. A. Now there's one process. A is very small. A equals 10, right? One instruction. B equals and you say E equals A plus B plus C equals 30. And you have an instruction called D equals A plus B plus C. So for this instruction, as we will learn later, there are so many operations going on. This is a simple statement like in English. Give a value of 10 to A, but in when you know, as you know that it is to be translated into machine code, right? Machine code, you have to translate. That will have more instructions and all those things have to happen in a synchronized way. Right? Supposing A happens, right? B takes place. We also get a value. C doesn't. Before C, C does, but later. Before that, this happens. Then what will be the problem? C doesn't have a value yet. No? A and B, okay. A has a 10, B has a 20, okay, but C, how much? C, because this is not done. Huh? If it's not there, how can this happen? Can't, no? Because of that, we have to synchronize these operations. These cannot happen before this happens. So that you have an internal clock, like there are people who are waiting to run a race, maybe different batches. One row is waiting, the another row is waiting. Then uh, there is a person who is having like a skipping rope. Turn it. When you turn, not the normal, the one person having it, two people having two ends of the skipping rope. I hope you know what skipping rope is. Otherwise, you can Google it up and find uh, not only images, even videos you will find. And two people having them and then having it horizontally, across the path where they are running, and you turn it in such a way that when it goes down, the rope touches the ground, the runners can go over it. And when it goes up, they can't. No, they will hit the rope. No? So the other batch will wait. Then the next turn, when it goes down, that batch will go. Third batch will go. That is like synchronizing. No one will go out of sequence. Another thing you can compare is an orchestra, music, a band playing or singing. Then there is a person called uh, the, who? The conductor. Conductor controlling. Conductor controlling the performance. So he has like a magic wand or something like a stick in his hand, and or even without a stick, he will do various operations like actions with the hand, and he will get the violins or the guitars for them to play either, or maybe let's take it the beat, tak, 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 like that. You have to sing according to that and the play according to that. So he will give the timing. If someone goes out of that time, then it will sound ugly. All have to follow his instruction in synchronization. That is what this is called. So for that, there's a clock ticking, tick, 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 tick. So every tick, there are how many, by the way, how many instructions can a computer carry out in one tick or 1 second, let's say? In 1 second, how many instructions? Well, my computer can carry out about 3 billion instructions per second. So per second, it ticks 3 billion times. Tick, 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 tick. In 1 second, 3 billion times. With each tick, one instruction is carried out. Now we get the idea. The first is an internal clock that controls the cycles of activity within the processor. So within the processor, it will control how many, the first one first, second one second, like that. And it's so fast. Even if you put 3 billion instructions, it will finish in 1 second. Well, then you might wonder, why does the computer take so long for some programs? That is because what it outputs, the peripherals are not so fast, like the screen, the printer, or the other in things. They are not so fast. So if you say count 1 to 3 billion, it should show, no? Just as you click run, it won't show 1, 2, 3. It will just say 3. The 3 billion number will appear on the screen. Why? 1 second. But it won't happen. You will see it running, no? 1, 2, 3, 4, 5, 6, 7, 8, 9 very fast. But you will see that is because to display it takes time. Takes time. So it can't work according to the CPU speed. But the CPU inside the CPU, this will do. Otherwise, it doesn't matter because again you might ask, so what's the use? The CPU is very fast, but the peripherals are slow. Then what's the use? Why do you make so fast, so quick, so speedy processors? Because of that speed only, you can do multitasking and various things. Because it can serve many applications at the same time because of that speed only. Each application will think that the CPU is serving only that purpose. That is the speed. So this will control the cycles of activity within the processor. The other is the system clock. System clock. System is the whole computer that controls activities outside the processor. So it's very important that now itself, at this moment, you put a lock into this, put a lock into the clock so that you will remember which clock is which. So internal clock, imagine that we are learning about the CPU now. So it's in the CPU. System clock, when you say system, do you know the system unit? Some people, of course, for that big box, they say CPU. That's wrong. CPU is the processor, it's a small one. But the big box containing the hard disk, the power supply, DVD drives, all those things, that's called the system unit. So the other is the system clock that controls activities outside the processor. So now you know it. No? Internal clock is in the CPU, system clock is in controlling the whole system. That's different. The CPU will have a defined frequency. So the frequency is defined beforehand for its clock cycle, which is usually referred to as the clock speed. Clock speed is depending on the CPU, not the system clock, the internal clock, CPU speed. The frequency defines the minimum period of time that separates successive activities within the system. Right, so then look at these key terms. Again, internal clock and system clock. Internal clock is, it controls the cycles of activity within the processor. Let's make this a little bigger. Again, controls the cycles of activity. Cycles mean like hertz. Hertz. Have you